So a few words about the key reactions. This is not any complete list, but like few ideas about the functional groups that are relevant for making liquid biofuels. And here's a table that describes the most, not all, but most common and functional groups relevant for these biomass components. So double bond containing, so alkenes, alcohols have this hydroxyl group, OH group. Ethers, like in sugars, have this oxygen bridge. Aldehydes and ketones are so-called carbonyl compounds, and they have the carbon-oxygen double bond. Aldehyde has it at the end of the chain, and ketone has in the middle of the chain. Then carboxylic acids can be found, for example, in the fatty acids. So there is this carbon oxygen OH. This whole unit is called carboxylic acid functional group. And when carboxylic acid reacts with an alcohol, it forms this ester that is found in the triglyceride structure. And there are several other functional groups that I have excluded from this slide because these were the key structural units that can be found on those common biomass molecules. And the thing why this is interesting to identify or important to identify the functional groups, even in these quite complicated molecules, is that organic molecules tend to react through these functional groups. So this aldehyde group in a smaller molecule and in a much larger molecule, they tend to behave in a predictable way, in a similar way in reactions. So that's why it's good to identify if your biomass is rich in carboxylic acid, so you only need to open the organic chemistry textbook and take the chapter of reactions of carboxylic acids, and you'll see what chemicals, what materials you can produce from that carboxylic acid containing material. So you don't need to study each of those tens or hundreds of molecules necessarily separately. You can detect the functional groups and at least to some extent predict what are the probable products from reactions of these molecules. So here are the same things once again. So hydroxide, aldehyde, ether in the sugars. Triglycerides are basically esters and might have alkenes. Carboxylic acid if they break down, hydrolyze, and then you also get that alcohol glycerol part there. So these are potential functional groups. Lignin, did we have here? The aromatic ring is missing, sorry. Yeah. So it's this 6-ring structure what we saw in connection to lignin. Terpenes have double bonds, and that's in a simple way. These. So few of the typical reactions here. This doesn't cover everything. So for example, this carbon double bond is nicely reactive in that way that you can convert it into various different chemicals. So that's a good reacting group. It doesn't react too fast, it doesn't react too slow, but you can you have lots of possibilities to make different chemicals out of this carbon double bond. Aromatic ring is slightly related to carbon double bond because you can also like carry on hydrogenations into aromatic ring as you can readily do it on a double bond here. So, but chemically or to a chemist, these are different functional groups. Aromatic ring is more difficult to reduce or to hydrogenate, but it's possible with higher temperatures, with stronger, better, different catalytic materials and so on. Also the terpenes that we went through, there is this same functional center that can be hydrogenated. And in making of fuels, so the hydrogenation or hydrotreatment reduction, sometimes called, it's quite common reaction that is utilized in making of fuels. Oil refinery produces its own hydrogen, and it's used in various parts of that processing. In simple terms, so if you have a double bond and you add hydrogen, so you kind of remove the double bond and make this saturated alkane instead of alkene. There's only one letter difference, E instead of A. But this often requires a catalyst to happen. And in making biofuels, so if we think about hydrotreatment, for example, this HVO, hydro-treated vegetable oils, which are the best quality diesel components that can be made out of biomass. So there one is using a catalyst to remove oxygen functionalities with that similar reaction, but it's a hydrogenation. I have a graph about that particular example few slides later. But I was planning to also tell you something about catalytic materials. I have to now think how much is really relevant, but in any case, so I'll come back to that next time on Wednesday, a little bit in detail. But majority of the industrial catalytic materials are so-called heterogeneous, so solid catalytic materials that are used, but a little bit more on that later. This is not that interesting, I think. It's pure organic chemistry. Here you'll see one example of this heterogeneous hydrogenation catalyst. So these industrial hydrogenations are done with hydrogen gas, not like some reduction agents like in, I didn't have it here. Okay, there are chemicals like sodium borohydride and such, which are the reduction agents, but those are expensive and sometimes difficult to handle. So this fuel production and industrial scale applies this gaseous hydrogen, but it's very inert towards chemical reactions if you exclude the explosion or combustion of hydrogen, which happens rapidly, but other hydrogenations or hydrogen reactions do not. So you need the catalyst, which speeds up reactions. And what happens in these solid materials? This is an electron transmission electron microscopy image of a real catalyst. I have used this in my research some 20 years ago. So this lighter gray material is aluminum oxide, which is the typical. It can be catalyst as such in some reactions. It has mildly acidic properties, so it can sometimes catalyze reactions. But in this case, it's only providing the support or the surface where the tiny platinum metal particles or nanoclusters are deposited. So these darker areas are those, in this case, platinum metal particles. And here you'll see the resolution of the microscope is quite nice. So you'll see these tiny dots are individual atoms. So these are quite large clusters, maybe some 100 atoms or so. But what happens in the hydrogenation is that the hydrogen adsorbs on the surface of this metal. Also the reacting component adsorbs. They combine on the surface and then they desorb and leave the surface, and that's how it works in molecular level. And the diameter of these is just a few nanometers. But these, like I said, so these are fairly large particles. One can work with much smaller ones as well. It depends very much on the reaction that you are carrying out. So this, I don't know if this works, but this represents that active metal site where hydrogen adsorbs, so it sticks on the surface, then it dissociates, or now it left, but it basically dissociates into H2, forms 2 hydrogen atoms on the surface, and these are the active species that then stick to the double bond and form the actual hydrogenation. So the reactant goes in, picks up hydrogen atoms and leaves. The mechanisms can vary. There are several alternatives, and I will not go into that details, but that's basically how quite many of these industrial reactions take place, not just hydrogenations, but also this Fischer-Tropsch chemistry, and wherever there are these heterogeneous catalysts for purification or for some other reactions. So this can represent what happens also there. I said that the aromatic compounds, now you'll see the 6-ring phenyl ring structure. So these can be hydrogenated, but not that easily. So here is a carbon double bond that can be easily hydrogenated. But if you want to also hydrogenate this aromatic ring, you need another catalytic material. Palladium is not good, but rhodium, I think, would do the job. If here is, yeah, here's an example. So platinum is stronger than the palladium, is least active. It's a good thing, because if you want to selectively remove this bond, so it can be done with palladium. If you would work with platinum, so it would reduce aromatic and double bond and so on. And if you need a stronger reduction agent, so rhodium metal is even more potent reduction agent for these. But this just illustrates that there are very many catalytic materials. The actual catalytic active material is in this case that different metal nanoparticle, but then the whole catalyst is composed of that support and promoters and many textural details that are built to the molecular level. So, but maybe something more about that next time. That was the addition of hydrogen in order to remove these double bonds. But the hydrogen in this connection also is closely connected to this the HVO process. And the idea there is that you want to remove oxygen from that hydrocarbon biomass material. It improves the fuel quality if you can remove some of the oxygen. And here are two reactions that can help you to remove. Here aldehyde group CHO can be converted to hydrocarbon and you'll get carbon monoxide. So this is called decarbonylation. And then the other alternative is decarboxylation. So this is carboxylic acid converted to carbon monoxide, and then you get an alkane. And where these reactions are happening is that this is the hydrodeoxidation, or actually it could be in this HVO process, hydro treatment of vegetable oils. So here's a vegetable oil or triglyceride structure. So if you want to make a good diesel fuel or fuel component, so you want to have these hydrocarbons. So this contains only hydrogen and carbon. These are good components. So you don't want these oxygen or these esters that are in the vegetable oil. So, and you can remove it with the help of hydrogen. And here is the decarboxylation reaction. And here basically, was it here correctly or the same? No, this is different. Well, in any case, so when you treat this with hydrogen, so you break this molecule from certain places, and this longer hydrocarbon chain comes from that fatty acid part. It also removes that double bond here. Then when hydrogen reacts with oxygen molecules, you end up with water, and this glycerol part, this 3-carbon chain, when you remove the oxygen, so you get propane. So you get this better quality fuel components. Here you can do decarboxylation, so you remove carboxylic acid. You also get these good long hydrocarbon chains. And these are reactions that can undergo under same conditions. So CO2 reacting with the hydrogen, forming water and carbon monoxide. Carbon monoxide and hydrogen can also produce methane and water. But we come back to this still a little bit later when we talk about this HVOs, hydrotreated vegetable oils. These functional groups also that are in biomass, so undergo many other reactions in addition to hydrogenation. And hydrogenation is one group of reactions that are called reductions. Opposite to reduction, there is oxidation. So reduction is something that is illustrated here. So you can convert carbon-oxygen double bond with the help of reduction. That could be catalyst and molecular hydrogen, like in these hydro treatment things, but it can also be some hydrogen donor or reduction agent, what I mentioned earlier. But carbonyl group converts to alcohol in aldehyde, and the same thing can be done also in ketone. And these aldehyde and ketone groups could be found in biomass. So if you want to convert them to alcohols, it's in principle possible. Oxidation is the opposite reaction. These examples are not the best. Like I mentioned, I don't have the program to draw these molecules myself, so these have been copy-pasted from all sorts of materials. But this oxidation is the opposite thing. So in the previous slide, there aldehyde and ketone were reduced to alcohols. So if these are oxidized, so these go towards carboxylic acid. And so you can go from alcohol to aldehyde to carboxylic acid, that's oxidation, or you can go from carboxylic acid to aldehyde and in principle to alcohol, that's the reduction stage. Here is the roughly the same thing described, just like in primary. So alcohol reduces to aldehyde and to carboxylic acid, and reduction happens in the opposite direction. Dehydration, that can also be utilized in the biomass treatment, so in principle. But if you have an alcohol and you would for some reason want to get back the double bond, so this is the opposite to hydrogenation is addition of hydrogen, making of alcohols. Dehydration is like removal of hydrogen. So you end up with that double bond here. This is then addition of water molecule, or so here is a carbonyl group. This is something that you find in the sugar molecules. So they can form these diols or react with water to form, for example, hydrates. And this is the similar diol that was here. But I had some idea related to this. What I wanted to say that this same reaction, hydration, so it can happen in different mechanisms, and this is the connection to different catalytic materials as well. So the similar product can be made with different type of catalytic materials. So this is base catalyzed addition, and here you'll see acid catalyzed addition. Product is the same, but mechanism different. And I already touched the catalyst topic a bit. So generally there are different types of catalysts in converting this biomass if we skip the pre-treatment steps and so on. So for example, this biodiesel, this fatty acid methyl esters, so that can be made using triglyceride and methanol and base catalyst or an acid catalyst. you can make the similar product but with different types of catalytic materials. Then so this would be example of homogeneous catalyst because it would be dissolved in that liquid phase. When we talk about the heterogeneous catalyst, like that hydrogenation catalyst, so that would be heterogeneous catalytic material that it's not dissolved in, so it's not dissolved in the liquid, or it can work with gaseous reactants being in solid phase. Then we have a third type of catalytic material that is common in biofuel production, and it's biocatalysts or enzymes or yeast. Yeast has enzyme which converts sugars into ethanol and carbon dioxide. So that's very commonly used also. But these are all examples of catalytic materials that speed up production of biofuels or generally reactions. Acetal formation is that this was reaction with water. So the last one, I think, is the addition of alcohols, or the sugar contains these carbonyl components, and if you have alcohol or this hydroxyl group, so it can form acetal structures. And the connection here to biomass is that this is basically the reaction how you could make these lignocellulosic polymers. And how it happens is that I have the glucose molecule here. So in that glucose molecule, there is that aldehyde, that carbonyl group, and in that long chain, sugar chain, hydrocarbon chain here, you have plenty of hydroxyl groups. And these basically react within the same molecule, so it's intramolecular reaction, and then you'll form these, I don't have slide here, sorry. So then you form this cyclic, like pyranose, furanose structures of that sugar. But if you have those ring structures of those sugar molecules, pyranose and furanose, so these same reactions can happen between different, so intermolecular reactions. So then you form these starch or cellulose polymers when from another sugar molecule's OH group reacts with another molecule's aldehyde group, and then you basically, that's how the polymers are built, or at least on a molecular level. So here it says a cellulose is formed by joining glucose molecule with removal of water, and basically this OH group reacts, binds to this carbon and releases OH and oxygen, and that's how these polymeric bonds can be formed. The ester chemistry is related to this making of biofuels, at least to some extent. So esters can be made again like organic molecules or biofuels. Biomass molecules can be made from different starting materials. So there is not only one route to make ethanol. You can make it from different starting materials. Usually it's made from those which are plentiful, which are the cheapest ones, easiest to convert. But in organic chemistry, you have several alternatives. Some of them are not really viable economically, but can be made in principle. So typically carboxylic acid, and this is very common, carboxylic acid and alcohol reacts. You need a certain catalytic material. This hydrochloric acid is an acid catalyst and it catalyzes the reaction. Then you make an ester and release water. So this is how you make esters, and triglycerides have basically reacted with alcohol and 3 fatty acids. So this similar type of reaction is there behind. Maybe not exactly, but it could be. This is then the reaction of making that biodiesel, fatty acid methyl ester. So what happens is that we have the triglyceride, the fat or the bio oil, and we have some alcohol, in this case the simplest and the cheapest, methanol, 3 of those. We need, in this case, we need base, or we can also use acid catalyst. So what happens is that this methanol reacts with this triglyceride. It breaks these ester linkages and it releases this glycerol here. And in the same process, when there are these fatty acids being released, so the free alcohol reacts with those fatty acid ones and forms these methyl esters. So basically this reaction happens there, or there are breaking of triglyceride and then the released fatty acids, carboxylic acids, react with the available methanol, making that biodiesel. So therefore, in biodiesel synthesis, so you'll end up with this glycerol side product and the FAME methyl ester desired products that are can be used in diesel engines or blend diesel fuel to some extent. It will be the bio component in there. I think this is not, I don't know why I have included it in here. Okay, here I had this. I thought that I included this here. So it's a little bit repetition, but this carbonyl group and alcohol can form these acetals, and basically that was what I tried to say, that it happens when the sugars form these cyclic structures. So I had here picture about it. So this reaction takes place. So it's hemiacetal formation with the alcohol and the carbonyl, and this then you form this ether linkage that you find in these polysaccharides materials. So this reaction is rather simple, but it can make these biopolymers. Here is a just picture of how it forms with glucose and fructose, like within the same molecule, but it can also happen so that it forms between different molecules, and this ether linkage forms. I don't have very representative pictures about this. Maybe I can try once I get the program running, so to draw some useful. But to summarize this, so there are we have now looked through biomass itself, and if you think what type of functional groups can be found in that biomass, so in principle there are many reactions or possibilities that you can react with these functional groups and make some products that are, let's say, usable as biofuel synthesis, or that the products already are or can be biofuels as such. Here was just a list of certain reactions that we covered today, and it's by no means complete list. There are really many reactions and possibilities, but some of these you'll find in connection to making of biofuels. So and I try to make just one slide here, the chemistry of biomass conversion. We'll see when we study next in next week. So we start to look at the individual processes. So we'll take a look at how this biomass is broken into monomers or smaller pieces. It can be done by different pretreatment methods, or it can be hydrolyzed. So that's also breaking the polymer chains into smaller pieces, or it can be done using temperature, high heat. So we can pyrolyze, and pyrolysis breaks the biopolymers into different, quite many products. And gasification breaks it to really tiny components, like tiny small hydrocarbons, carbon monoxides, and hydrogen, and such kind of very small building blocks. But the idea is that we obtain the biomass, we treat it so that it can be then converted into some useful products. And during the course, we, for example, take a look at how the sugars, typically the 6-ring glycose, can be fermented to bioethanol. There are certain microbes that also ferment other sugars than glucose, and so on. But that's one example. So this glucose can be obtained from cellulose. So that would be then the second generation biofuel. So you utilize sawdust or some biomass that is not food for anybody. You'll hydrolyze it or pre-treat it so that it eventually breaks into those sugar monomers, and then the yeast can ferment it to ethanol. The first generation approach is that you'll get the glucose from these sugar producing plants like sugar beet or sugar cane, but those are edible materials, so this is not the preferred way. Another thing is that if you end up with this pyrolysis oil, it's a mixture of all sorts of hydrocarbons, alcohols, aldehydes, whatever. So that as such is very low quality fuel. It's not useful, but for maybe combustion or burning like for heat, I mean, not for any transportation means or for longer storage. So therefore, you need to upgrade it, and depending what type of components there are, so you can select the upgrading methods. but that we take look also a little bit later. And from gasification, you'll end up with the desired product is carbon monoxide and hydrogen. And this is called synthesis gas. And that is something that you can make quite many things out of it. Of interest is, of course, you can make methanol out from synthesis gas. You can make hydrogen, basically. And the most important thing probably in fuel terms is that you can make with Fischer-Tropsch reactions, you can make hydrocarbons. We come back to that at the later part of the course, but synthesis gas, this is source for carbon, this hydrogen is source for hydrogen, and in Fischer-Tropsch, basically it's a kind of a polymerization reaction where hydrogen carbon combine in the presence of catalyst, and you end up with the distribution of shorter and longer chain hydrocarbons. So that's like the way to go. So you break and modify the biopolymers. Eventually you get smaller, more usable fractions, the monomers that you can convert to useful products. Then triglycerides, so these fats and oils are a little bit different. So they don't require this breaking part like to similar extent. So if you have already the oil, so you can do the transesterification reaction with alcohol, methanol, the cheapest one. It works with ethanol and other alcohols, and you end up with this biodiesel. But if you want a better quality fuel, so you take the triglyceride, the oil containing material. It can be waste oil from somewhere, residue from slaughterhouse or whatever. If you do this hydro treatment, like according to those reactions that I showed a while ago, so you can make this higher quality product, HVO diesel product, and so on. So these are just some of the alternatives that can be carried on. So it all depends on what type of biomass, and you have several alternatives to treat different biomass. You have possibilities to make different types of products. And yeah, that's something that we start to look then